We're going to talk about designing shafts against failure in torsion. And for axial loading, we have done some of these problems. We have said, how do we dimension the cross-sectional area so that we do not exceed a limiting failure stress. We're going to do the same thing in torsion, and we're going to make some assumption about what causes failure, which are a little simplified. But for now, let's say that we want to design some torsional shaft. And the simplest design criteria that you can have against failure is that the stress in the shaft must be less or equal than a failure stress divided by some safety factor. That's similar to what you did before, right? I want you to understand that this stress and this thing are two different concepts. So this stress here, this is what you have in your structure. So this one is the maximum stress that exists in your structure. So this is the max stress in your structure. What does this depend on? It depends on what loads you have. It depends on the geometry of the structure. Maybe how big is the radius of the shaft, how long is the shaft, what loads you have. And if it is a statically indeterminate shaft, it can also depend on the stiffness of the material. Because if you have, for instance, a torque in the middle of a shaft that is made of one material on one side and another material on the other side, how much each of the two halves of the shaft carry depends on the properties, on the material properties of the shaft. So it depends on the loads, on the geometry, and for statically indeterminate problem, it can also depend on the material properties. So this one is what's inside your structure. This thing, tau F, is a failure stress, and this is a material property. So this has been measured by somebody that has loaded a shaft up to when it fails and noticed, when the shear stress reaches this level here for this material, the material fails. They measured it and they tabulated for you, so you have it available so that you can design the structure so that your structure does not fail. Okay, so tau F is a material property and it's going to be, say, tabulated or whatever. Is that clear, the difference between these two? So how do we design something so that it doesn't fail? Of course, we want to limit our maximum shear stress, right? So how do we calculate the shear stress in one point of the material? The shear stress at some point along the shaft at some radius r is going to be equal to the properties of the material there, G of x and r, times the shear strain at x and r. So if I substitute for the shear strain, I find G of x and r times r d phi dx. And so that's equal to G of x and r times the radius times the torque at that section divided by GIP effective on that section. Okay? So you want the maximum of this to be less than your safety, than your failure stress divided by some safety factor, 2, whatever. Depends on how safe you want to be. Okay? Now, you see that the maximum tau typically occurs at large radii if you have a composite section like you have in your homework, in which your G is different from the inside and the outside. So you have a core that's stiff and an outer radius and the outer shell that's soft. It may happen that because in the core, you have a higher G. You may have your maximum stress inside the structure, right? But in general, now to simplify our life, let's consider a solid shaft. So from now on, let's consider just one homogeneous shaft. So if the shaft is homogeneous, then your tau max is going to be at the outer radius. So if your shaft is homogeneous, G is just a constant. G and G, these are the same G, so they cancel out. So if the shaft is homogeneous, tau max is going to be equal to R times the torque at section X divided by IP of X. So we want this to be small. We want this to be small. So what do? We see it becomes bigger with the radius. So does it mean that we want a small radius? Is that what we want, so that we have a small tau? Is that a good idea? Does that seem good? No, small radius, no. That's like one of those death things. No, death upon us. No, not small radius. Why not small radius? Because the radius also enters into this guy over here, right? So if you substitute the value of IP, you find that tau max is equal to the torque divided by pi r to the fourth over 2, so there is a 2 on top, and 1 r to the fourth cancels with that, so you get pi r cubed. Right? So this one is the maximum stress for a homogeneous shaft. So if I want a small stress given a certain torque, I want to make my radius big, right? Okay. So this is a homogeneous shaft, a solid. So I want big R.
You want big R because it's in the denominator?
Yeah. So given a certain torque, I want a small stress if I have a big shaft to carry that torque.
You want a small stress? You want to maximize the stress?
No, this is not. Go back to the concept. This is the maximum stress that is inside my structure, right? This is what is in the shaft, which is a torque T, and at that cross-section has a radius R. The tau max at X depends on the torque that I have on that section X, and it depends on the radius of the shaft at section X. The maximum, if you plot the stress as a function of the radius, you find that your stress is maximum at the other radius because the stress is linear with the radius, right? If you look at this equation here, you see that your stress varies with your radius linearly. So the stress is going to be small in the middle, get bigger and bigger and bigger. On section X, the maximum stress that you have is this. You do not want the shaft to fail. So you want this tau max to be smaller than a certain amount. Your safety, 50 MPa, 100 MPa. You want it smaller than 100 MPa. You want the maximum stress in the shaft to be less than a given number that keeps the shaft safe. Okay? All right. So if I want the stress small, I want the radius big. That is the same as what we had in axial loading. If I have to carry 10 kilonewton and I want the bar not to fail, I want a big cross-section so that I have small stresses on the cross-section, right? What has changed now is that I can play with geometry. I can play with geometry because now, remember that what's in the denominator is IP, which is not just a cross-sectional area, but is the integral of r squared dA, right? So if I want the stress to be small, what I really want is I want to use the area wisely. You see? Because I want a BP. If, say that I have limited weight that the shaft can have, which really means I have, given a certain material, means I can only have a certain cross-section, right? How do I use that cross-section is important in torsion. It's not like axial loading that I could make it into the shape of whatever, a butterfly, and it would carry the load the same shape as a heart would carry, the same shape as a circle would carry. It wouldn't care what the shape of the cross-section is. When I work with torsion, because I have this part here that matters into the stress, I can play games with that. So to show you what I mean is consider the following two cross-sections. Say that I make a cross-section solid. Actually, let me make it smaller here. Otherwise, I'll take the whole board in circles. OK, I consider two cross-sections. The first cross-section is simply a solid shaft of radius r. OK? But I also consider another cross-section. I consider a cross-section which has a radius of 2r and a thickness r over 4. OK? So these are two possible cross-sections of the shafts that I can have. Homogeneous, made of the same materials. This cross-section is hollow, and this cross-section is solid. OK, so the cross-sectional areas are, in this case, is pi r squared. In this case here, I'm going to make the approximation of thin wall, although this is not really very thin, is the circumference, which is 2 pi times 2r times the thickness, which is r over 4, which is also equal to pi r squared. So the cross-sectional area of this cross-section and this cross-section, the areas are the same. Now the IP of the cross-section, in this case, is simply pi r to the 4th over 2. In this case, if I make the approximation of the thin wall, it is this area, pi r squared, multiplied by 2r squared, right? So that's 4r squared. So I have 4 pi r to the 4th. There is a factor of 8. There is a factor of 8 on the IP that I gained by making a hole in the middle of my shaft. You see? And my stress, if I calculate my stress, tau max, when I multiply this by the torque and by the radius, I get, it's going to be equal to the torque times the radius times this. So it's going to be torque times pi divided by 2r cubed. And this one here is going to be torque. Now the radius is 2r, so I lose one of the two. So it's going to be torque divided by, torque divided by, times 2. What am I saying? 8. So I get torque divided by 8. Pi 2. Well, that's the problem. The 2 goes in the top here. That's why it didn't work. So torque divided by 2 pi r to the 4th. So now the ratio between the stresses, there is a factor of 4. So the factor of 4. So this one here is better than that in terms of limiting the stresses by a factor of 4, right? So you're like, OK, this is fantastic. I know what I'm going to do. I'm going to be the best designer of shafts in torsion ever, right? because I'm going to make it bigger and bigger and bigger, thinner and thinner and thinner. So you say, OK, so I know what I'm going to do. I'm going to, instead of having this one, this is no good. I'm going to make this one is better. So if I make a calculation, this one is going to be even better. And this one is going to be even better. And I keep going and going and going. And I have this humongous shaft with a very, very thin wall. And you're like, oh, this is so effective, except for the fact that it takes up a lot of space. Oh, sorry, that should be third. Sorry.
No, but in the pi squared to the left.
No.
Right there. Oh, right there.
Oh, that's a 2.
But shouldn't the pi be on the bottom as well?
Yes. Sorry. OK. All right, so let's go back to my fantastic design idea. I keep making them bigger and bigger and bigger, with the wall being thinner and thinner and thinner. And according to my calculations there, the more I do this, the better I am in terms of limiting my stresses. So why don't I do that? Did you ever do like a soda can and show your strength by taking this thing and doing that? Right? What happens? That's a very thin wall shaft. What happens when you do that? If I take the soda can and I just twist it, what happens to the soda can? It makes all wrinkles. It wrinkles all over the place. After you finish twisting, your soda can looks like a mess. Like that. Right? You do not want a structure to do that. Why does it do that? Why do you think it does that? You're twisting it. We talked about buckling before. Remember, we talked about buckling, and I said, if you have a thin, slender bar, and you put it in compression, well, it buckles out of space, because it says, I don't want to be straight. I can accommodate this load by bending around instead of being compressed axially. Remember, that's a buckling load. If you push too much or something, it thinks it's buckle. Now, what happens when you do the soda can is something that looks like buckling. You pull, you rotate, 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 all of a sudden, boom, it goes. And it wrinkles all over the place. So this is a buckling instability. We're going to go, and buckling is very bad. Another death. There it is. The death from buckling. Okay? So you can only go to some extent to this idea of making things thinner and thinner, because if you make them too thin, that happens. The other thing you have to be careful about torsion, so this is warning number 1. Warning number 2 is the extent to which what we do in 201 applies. So in 201, we do solid shaft or circular shaft, all nice and axis symmetric. Let's say that instead of solid, you have something like that. And let's say instead of having something round, you have something like that. How do we deal with this? Well, things get a little more complicated. But the analysis that we do for 201, if you kind of make this round, it kind of gets you more or less in the right place. If you have something thin, well, there's going to be stresses that are flowing around the thickness of the wall, just the same as the stresses are flowing around the thickness of your little round shaft. So this part here is different from 201, but kind of okay, the concept that we have. The things that you have to be worried about are things that look like that. If you have something which has an open section, like that, and you put it in torsion, open section like this in torsion, they're horrible in torsion. These are bad in torsion. If the section is open, it's bad. which means that you have to worry about failure along lines like this in torsion. So anything that is like a box, something like this, in torsion, bad. Open section, are bad. You have to think of stress, the lines of stress that carry the load, like a flow of a river. Okay? So in torsion here, the flow of the river is all around, and the flow of the stress all around gives you the resultant torque. Here, your stress is like, has to do this, go around here, come back here, do this, and come back like that. That's how it carries torsion. Like this, down and up and down and up. Lines go this way here, that way there. What a mess. It's like a traffic jam. Very ineffective. Okay, so if you design things in torsion, not open cross-section. So, the last 2 minutes, I want you to, a little more than 2 minutes, I want you to pull out your little green things. Take your little green little net things, because I want to tell you something about this buckling thing a little more. We said that buckling has to do with compressive loads, right? Compressive loads. But this is torsion. Torsion has to do with shear, right? What is the compression? Why would there be buckling in shear, for goodness sake? Well, up to now we did two things. We did axial loading, in which if we had something that looked like this, we put a normal stress on it, and the original shape becomes elongated. There is an epsilon axial. There is an epsilon transverse. And we see that the length change but these angles stay the same. If this was a if this was a square, this is a rectangle, and these angles stay the same in axial loading. See, a square, if I pull it in axial loading, becomes a rectangle, and the lines remain parallel. That was the whole thing in axial loading, right? And then we did shear and torsion. So this is axial. Then we did shear and torsion. And in shear, we had something that looked like this. And we said, OK, we shear it, exaggerating a little too much. We had something that looked like that, remember our block, and we sheared it by a certain angle. And so see, the length remained the same. So in shear, the length stayed the same, but the angle changed. And we said, OK, this one here, how much stress I put, is connected to the strain by two properties, E and nu. And we said, in this case here, the shear stress that I give is connected to the shear strain by another property, G. We take these two worlds, one in which things get longer and shorter, but the angles stay the same, and this other world, which is a world in which I shear things, the angle change, the length do not change, and I put a line between them because I do one at a time. But now take your little green tubes and pull on it, and look at the lines in the walls. Look at those angles. Do they stay the same? I'm doing tension, right? In tension, aren't things supposed only to get longer and shorter, and the angle do not change? Well, it's not working that way, right? If I have something in tension like this tube, and I look at the lines that maybe start like that, once the tube gets longer, now the lines look like that. And the angles here between the lines the angles between these lines that maybe used to be square there, now those angles has changed. By looking at this thing, you see that if I pull in tension this way, if I rotate my head, and I look at a 45-degree angle, in that world, in the 45-degree rotated world, there is shear. So if I have tension along this axis, there is shear at 45 degrees. If I do shear, and I look at these lines, look at this diagonal. This diagonal gets longer. See how much longer it gets? This diagonal gets shorter. So if I do shear, there is tension and compression at 45 degrees. So if I do torsion, and I take my hand here, and I take this thing and twist this way, and I twist this up, right? So I'm doing that. I am taking the shaft here, and I am rotating. Let me make angles. I'm rotating this one down and this one up. So I'm doing that, rotating this down and this up. If I make a line between these two things, when I do that, see the lines, this line here, that's get longer after I rotate it. You see? I get farther away on that diagonal. Instead, these two guys that were a certain distance apart, this one and this one, when I rotate it, see, they get together. See, they get together. So along this line, I have tension. Along this line, I have compression. See? And that is why when I twist the soda can, it buckles on the 45 degrees on the diagonals that gets in compression. Okay? So these two worlds talk to each other. They talk to each other. And we're going to do the talking at the very end of this class. Like the last lecture, when you think you're free, we're going to go back to stress and strain and understand how shear and axial loading are related. And because shear and axial loading are related, I leave you today with an amazing fact, that G is equal to E divided by 2, 1 plus nu. They are not independent. Axial loading and shear talk to each other, so the property in axial loading are connected to the property in shear. This is life, the universe, and everything. 43. Okay? All right, this is like cliffhangers in structural mechanics. Ta-da! Could it be? It is. Okay? All right. So we are done with torsion. You can finish up your homework for torsion for Thursday. And on Thursday, we start bending. Okay? So the pace goes, you're like one of those silent movies. Everybody's running. Okay? So digest torsion, digest it quick, because, hey, we're moving on. Okay? All right. See you Thursday.